Welcome to qnawire.
So in this problem, the key is drawing a correct free body diagram of the object so we can see the forces that are acting on it. So if you think of a person sitting on a chair, there's a weight due to gravity, which is pushing straight down. And in the exact opposite direction, you have the normal force. And if the chair is being pushed to the right with some force, then if there's friction involved, friction will always be in the opposite direction of the movement. And here, since there's motion, it'll be kinetic friction. Whereas if it's not moving, it'll be static friction. So here we have some car that's trying to accelerate up a slippery slope. And we want to find the acceleration given two different values of kinetic friction. So we're given the coefficient of kinetic friction. The first value is 0.12. The second one is 0.05. So the first thing you want to do is find the angle of that slippery slope. And we're given this little tiny triangle where the bottom is 10 and the right is 1. This is the angle we want to find. So to do that, we can just do tangent theta, which is 1/10. And to get rid of the tangent, you do tangent inverse of both sides. So on the left, we get theta equals tangent inverse 1/10. So theta, the angle of the slippery slope, is 5.7 degrees. Next, we want to draw the free body diagram so we can see the forces involved on the car. So this is the car going up the slippery slope, and it'll have weight straight down. And again, this is due to gravity. And weight is just mass times gravity. And since the car is at an angle, the weight will have components. So we have in the y-axis, we have wy, and then in the x-axis we have wx. And notice that wx is pointing straight down the slope, meaning the weight is the actual movement of the car. The weight is trying to push the car back down the slope. So if the car is trying to go down the slope, even though it is accelerating up, the friction is to the right, because it's in the exact opposite direction of the movement of the car, which is the weight in this case. And of course, the car is trying to move, so this is kinetic friction, and kinetic friction is mu k times the normal force. And the normal force is in the exact opposite direction of wy. And from this little tiny triangle that we have here, we can find wx, which is wx is mg sine theta, mg being the weight, and wy, again, weight times cosine theta, and weight is mg cosine theta. So now let's look at the forces in the x direction, because that's where the acceleration is at, since the movement is in the x direction. So if we say that going down the slope is positive, and straight down is positive, then looking at the forces, we have wx pointing left, positive, the kinetic friction going to the right, which is negative. So we have, again, wx, which is mg sine theta, minus kinetic friction, mu k times Fn, equals mass times acceleration, because the car is trying to accelerate. So from here, what we don't know is F of n, and we're trying to solve A, the acceleration. And going back to our diagram, we see that the normal force is in the y-axis. So if we look at the forces in the y-axis, and we can solve for F of n and then plug it back in to our equation. So in the y direction, we have wy pointing straight down, which is mg cosine theta, that's positive, minus normal force pointing straight up, so it's negative, minus Fn equals, and there's no movement in this axis, so we have 0. Now we can just solve for Fn easily, move Fn to the other side, we have Fn equals mg cosine theta. Now I can plug it back in to our equation right here. So now we have mg sine theta minus mu k times the normal force, which is now mg cosine theta, equals mass times acceleration. If you notice, the masses cancel out, which is a good thing because we were not given the mass of the car, and we can see just from our equation that we don't really care about the mass in order to find the acceleration. So we're left with the acceleration, this is what we're looking for, equals g sine theta minus mu k g cosine theta. So now that we have a general equation, we can plug in the coefficient kinetic friction values that were given. So the first one is mu k 0.12. So all we do now is just plug in our values. So we get acceleration equals, we'll leave gravity by itself right now. So g is equal to sine of 5.7 minus, so mu k again here is 0.12 times cosine 5.7, and of course we still have gravity here. So both sides have gravity, so we can combine these. So we're left with A is equal to minus 0.019 times G. But here we know that gravity is actually negative 9.8 meters per second squared, since his weight is trying to pull the car back down. So if we plug this in for acceleration, we get positive 0.19 meters per second squared. And this tells you, since it's positive, that the car goes up the ramp, given this coefficient of kinetic friction. Now for the second one, it's the same thing. Now we just plug in our values, and here for the second one, mu k is 0.05. So we have for acceleration, A equals g sine of 5.7 minus mu k here becomes 0.05 times cosine, or times gravity, so 0.05 times gravity times cosine of 5.7. So again, we can combine them since both terms have gravity in it. So we have A is equal to positive 0.049 G, and again, gravity is negative 9.8. So when we plug this in, we have acceleration equals negative 0.49 meters per second squared. So for this value of the coefficient of kinetic friction, acceleration is negative, so the car goes down the slope.